I'd like to introduce our speaker this morning for giving us a talk on network-attached shell, nasty systems that store network-accessible shells. We've got Jacob Holcomb.
Hello. How are you guys doing? Okay, so I guess an issue I'm having with my wireless card I'll deal with when we get to the actual demonstrations. So as you were just informed, my talk is network attached shell, NASD systems that store network accessible shells. The purpose of this talk is to discuss the insecurities of network storage systems, hence storing network accessible shells. We're going to talk today about several things, but basically the insecurities of these devices and how they can be compromised. So really quick, who am I? I'm Jacob Holcomb. I'm a security analyst at Independent Security Evaluators. I exploit software. Why? Because I love doing it. It's my hobby. I get to do it for a job. It's like the best thing in the world. Okay, so is this really important? Well, yes, it is. And why? 100% of the devices that I've evaluated are vulnerable to some form of exploitation. In most cases, the exploitation led to a full root compromise. And storage systems are not the only embedded device that have gaping holes or system deficiencies. As demonstrated by Craig Hafner last year here at Black Hat, he talked about IP cameras and how they were incredibly vulnerable to attack. I also put out substantial research last year discussing the insecurities of SOHO routers, where I published 56 CVE numbers for various vulnerabilities across like 12 devices. So really quick about the company I work for. I work for ISE, Independent Security Evaluators. We are a computer science firm who specialize in security. Our customers are basically Fortune 500 companies, and they hire us to assess third-party software products. And these products are normally used within their organization, and they bring us in to say, hey, is this a secure piece of software to deploy on a network? Another primary note is that our perspective is white box. So a lot of time when you hear pen test, you're thinking like network engagements and just attacking, a network, seeing how an attacker could get in from the outside. But we like to dive deeper into the systems and actually look all the way down to the source code level and try and uncover bugs that you may not find in a normal pen test. So yeah, that's that. All right, topics. So what are we going to cover today? We're going to talk about storage devices. What are they? The name is kind of obvious, but we'll just briefly cover it. The key players in the market, system functionality, so what these devices are, the purpose for them, and what functionality they offer end users. The exploit research and development, so the process of finding vulnerabilities and then exploiting these vulnerabilities to assume full control of the device. We will then talk about the absence of security from other embedded electronics with some demonstrations as well, and then some steps for remediation. Okay, so subject background. What are network storage devices? Well, as the name suggests, they are devices that store data. These devices are widely used in businesses for a multitude of purposes, some of which are to support the infrastructure of, let's say, virtual desktops or other file sharing databases. Who are users of these devices? Anybody from the small home users all the way to the large enterprises. And something that I'll talk about here that I find rather unique is these manufacturers, as they create the software for these devices, they're basically creating one package and they're deploying it across their low-grade devices all the way up to their high-grade devices. So you could have a $500 device running the same software as, let's say, a $25,000 device. That's a problem, especially when we're familiar with the trends of SOHO devices being updated by the manufacturer. All right, so some key players. Here are some manufacturers of devices that I assessed or did not assess, but they're some of the big names in the field. And then the consumers we've just talked about briefly, like home consumers, small businesses, large enterprises, things of that nature. So here's a quick list of the products that I evaluated during this assessment or during this research project. And actually, I'm still in the middle of uncovering and going through all the software. There is a lot of attack surface to look at in these devices and a lot of extraneous services that aren't necessarily needed, but I mean, that's up for debate. But here are the devices that I looked at. Every one of these devices is vulnerable to some form of remote compromise. And when I say remote, it's a network-based attack. So me being either on the same network as the device or being able to communicate with the device over the internet could compromise these devices. All right, system functionality. So these devices, I have a couple of them up here, are essentially like file servers. But even up to like the mid-range business device, they offer functionality that isn't necessarily needed. The primary purpose, like we've discussed already, is to store data and facilitate the access to the stored data. These devices offer a multitude of ways to configure them, some of which are Telnet, SSH, or HTTP. And the unnecessary services, the key service that I'm going to point out here is the Cough Cloud Cough. A lot of these devices, including this D-Link, offer a service called My D-Link, which essentially is a cloud service that takes the content on your device and allows you to access it anywhere, except instead of you performing like NAT on your router and having access to it over the internet, having to worry about a static IP address, D-Link is the facilitator for the service. So you would connect a D-Link, and then D-Link would connect to your device. And they do that through some form of dynamic DNS. And then application repository. So these devices are essentially all running Linux, and they have repositories of software that you, the end user, have the ability to install. You can either install blog software, you can install file sharing, music sharing software, etc. So pretty much you turn this simple one-purpose storage device, access my content, into this large hole on your network, we'll call it. All right, so exploit research and development. We'll quickly talk about the summary of the results. And as I stated, I'm in the midst of performing this research, so what I talk about here is in no way conclusive, and throughout the year, I will continue to release more research and more vulnerabilities and exploits for those vulnerabilities. We're going to talk about the testing methodology used. Just really quick, scanning and enumeration, how I figured out what was running on these devices, the discovery of vulnerabilities, and then the exploitation of said vulnerabilities. And then, of course, we will have various demos. I will be performing 3 live demos against 3 storage devices, 1 against another form of embedded electronic, and then I have 1 video for a device that weighed in itself about 30 pounds, so there was no way for me to bring it to this event. And then we'll talk about mass exploitation. So, preliminary results. A staggering 100% of devices are susceptible to root compromise. There wasn't one device that I looked at that I literally could not take over. At least 50% of those devices can be taken over without authentication, meaning that there is some form of authentication bypass, or the device, for whatever reason, has missing function level access control and doesn't perform authentication checks. That number will grow over time, but like I said, I'm in the middle of performing my research. This is a statistic I have right now. Currently, I have 22 CVE numbers assigned. If any of you have followed the research that I put out in the past year, I put out 56 different vulnerabilities in Soho routers and had 56 CVE numbers assigned for them. I can tell you these devices are going to surpass that by the end of the year. They're terrible. Okay, so testing methodology. Scanning and enumeration, vulnerability discovery, and then the vulnerability exploitation. So really quick, really simple, scanning and enumeration. Who's familiar with determining what's running on the network and how you may go about doing that? Using tools such as Nmap. Okay, so this is an imperative step to any assessment, whether you're hired and you're on site performing a network penetration test, or you're just performing an assessment, independent research like I am presenting to you today. So you would first need to understand what the device is running by default. And you can do that using a series of tools. My favorite and probably the most robust is Nmap. And I have Nmap output for actually a router, Verizon Fios Action Tech in the top left. Nmap basically will determine if a port is open through various methods for both TCP and UDP. If a port is then open, if you told it to check what service is running on that port, it'll attempt to fingerprint at the port. Assuming that the data sent back from the device you're scanning meets the internal fingerprint database of Nmap, it'll give you a best guess as to what service is running. Additionally, you'll want to confirm each of the ports reported by Nmap with another tool. And a great tool for doing that is Netcat, to where you can just basically manually connect to the port, send it data, and observe the response. And I have Netcat output below in the bottom right, making a GET request to a web server. So vulnerability discovery. All right, so assuming that you have this list of services, you may or may not know what they are. You now need to investigate them. So you need to look at the types of services that are running, like SSH, SMB, SNMP, anything else that may be on the device. Any obscure port that you may not necessarily know what it is, and try and understand what it's speaking or what its purpose is. If port 80 or 8080 or 443 was open, basically if you determine that a port was a web server, you're going to want to actually access that port and see what type of application, if any, is actually being served. If there is a web application, you're going to need to analyze the web application. And in order to do that, you're going to need to know, simple details like, okay, what type of application am I dealing with? Is it PHP? Is it ASP.NET? Is it Ruby on Rails? You will also then need to be familiar with the languages used on the client side, obviously HTML, CSS, JavaScript. Once you've compiled this data and it's been aggregated, you then can actually step back and look at the whole picture and determine how you're going to move forward in your assessment. Source code review. This is critical. If you're ever doing an assessment on anything, any software product, and you have the ability to look at source code or look at part of source code, like if you had header files that were available, take that information. You need to gather as much information as possible and understand how the application is working, in the back end. So I can't stress this enough. If source code's available, get it. You'll be amazed at the types of things that you'll find. You'll essentially could, start looking through the source code, realize that they perform authentication checks on 9 out of 10 pages, but page number 10 you can access without authentication. It's great. And then dynamic analysis. This is fuzzing. Are you guys familiar with fuzzing? Yeah, fuzzing's a lot of fun. Basically, it's just sending a bunch of peculiar input to an application and observing the response. Now, you can't just do like dev urandom and redirect it into an application. You actually have to speak its protocol and understand the underlying mechanisms of its speech, so to speak, or its dialect. Okay, so the types of vulnerabilities that I've discovered so far during my research are on the screen. The most prevalent would be command injection. Most of these devices, you literally can execute system commands. And depending on the avenue in which you can execute them, you could just take over the device. Excuse me. Cross-site request forgery. This was something that I talked about a lot with routers. Basically, this is a great hammer attack against web applications. If you, for whatever reason, can't access the application directly, or if the application is enforcing, authentication and authorization, you can try and leverage an attack against the client to, perform some action for you. Information disclosure, for the most part, this is probably a pretty benign vulnerability, but the information disclosed by these devices, or any device for that matter, can normally lead to a more successful attack and compromise. You may gain further insight into the inner workings of the device that you're attacking. You may determine that there are some additional services that are running that you can't directly interface with, but through some other protocol or some other port, you can. Backdoors. So backdoors are pretty common in embedded electronics, as we've discovered over the years. Within the past year, there's been several published from various manufacturers and routers, and there definitely are backdoors in these devices as well, which we will briefly discuss. Poor session management, deterministic cookie generation. So I will show here that there's one device that actually has a 16-byte cookie, but that cookie is generated in a way that is ultimately deterministic. And by looking at various cookies and determining the pattern of the cookies and using some reverse engineering, we're able to develop a attack that can determine a currently active cookie. And then direct reach reversal. So here's another common one amongst these devices. I mean, these devices are here to share and facilitate access to data. So it doesn't surprise me that there are tons of direct reach reversal vulnerabilities. And with these vulnerabilities, I've demonstrated that an attacker would have the ability to upload files to arbitrary locations in the file system or download them. That means getting sensitive configuration files that may contain passwords. That means putting your web shell, or some executable up on the device and then having the device execute it. I won't be demonstrating any of those today, but in the coming weeks or months, I will definitely put out some exploits for these types of vulnerabilities that I found. So the one backdoor that we'll talk about today is a backdoor account that was found in the Seagate device, which I don't have here. But once I compromised the device through command injection, we were running as root, as you can see. There was an undocumented account here. And if you've noticed within this file, the encryption used for the password is the old Descrypt. So this account, you could crack the password and then gain access to the device. This is some nasty stuff. And the account is in some form of leet speak. If any of you guys have any idea what they're trying to say in the leet speak, please tell me. I've been trying to figure it out for a while now. It's been a heavy conversation around the office. Okay, so here's the poor session management vulnerability that I was talking about. And there's actually quite a few. Really, in hindsight, the session management used by this ASUSTOR device is stronger than some of the others, which I'll talk about later. But this is definitely a large vulnerability. So on the left, in the black terminal, you'll see various cookies. And I've highlighted a couple of bytes of the cookie. And as you can see, they are pretty repetitive. Using Burp, I used its built-in sequencer tool to look at the effective entropy pool and to try and determine what character set these cookies were using and how often those characters change. And Burp estimates that its effective entropy is around 2 bits, which is very poor. So as you can see here, we have 16 characters, and characters 0 through 13 have very poor entropy, meaning they're pretty much static, or they change very seldomly. But the last 2 characters change frequently. Well, if you think about how random values can be generated, if you're thinking about, let's say rand or srand in C and how you might see that, a very bad pool of entropy would be to use the current time. Time is sequential, and you can determine every subsequent part of time, which, as you can see here, only the last 2 parts of this are changing. So it's very plausible that they were using time to generate this cookie, which we show here. So here's some very simple C code. All we're doing here is declaring a struct time of type timeval, and we're going to use this to get access to the current time since epoch. We're then calling getTimeOfDay with the address of the struct, and then not worrying about any of the time zone specific stuff, hence the second argument null. We're then going to print the seconds and the microseconds. So if you guys remember from up here, the first bytes being 53df, once we run that code, we compile it with GCC, we run it, the seconds, the first part of it is 53df. So already with this information, we know that they're creating these cookies based off of time. So further analysis in this device, it's a Suster device, tells us that sessions will only last up to 60 minutes, meaning that from any point, if we can determine cookies, if we can determine all of the cookies, within 60 minutes, there's a very high probability that we could guess the currently active session and then assume control of the device, just by essentially brute forcing cookies. So this is a severe vulnerability. All right, so I guess now we'll get into some of the exploitation details. We'll talk about specific vulnerabilities, command injection, cross-site request forgery, missing function level access control, and those types of issues are normally authentication bypasses or failure to perform authorization checks. And then a stack-based buffer overflow. Yeah, okay. So command injection. Without reading my definition on the slides, who's familiar with command injection? Like who's actually exploited it, or has, worked with some form of command injection? A couple of you? Okay. So as my slide says, command injection is a type of vulnerability that allows an attacker or an adversarial user to take operating specific commands, operating system specific commands, and inject them into the application. And this is achieved by the application taking the input from the user. They then don't perform any sanitization or validation of said input. They put it right into a call to like system or exec, and it gets executed by a shell interpreter. And if you, for whatever reason, are able to inject, shell meta characters, such as backticks or $, parentheses, anything that will perform standard command substitution or chain commands together, ampersands, semicolons, you would then have the ability to escape the confinement of that currently executing command and execute a command of your choice. This can be very severe, or is very severe, and it's not can. So really quick, developers, because I know there's probably some developers out here who develop secure software or try. If for whatever reason you need to interface with the operating system, you should try to avoid calling shell commands. And to do that, you can basically either roll your own, which I don't recommend, or use a library that contains the functionality you're trying to achieve. An example that I like to use, that I used last year in my talk about routers, was getting the current directory listing of a directory. And if for whatever reason a developer chose to call system and then ls and then a variable that's controlled by the user, they could execute arbitrary commands. But a safe way to do that would be to call the listdir method that's available in the OS module. And that will essentially only list the contents of a directory specified by the argument. And you don't have the ability to execute commands because they're handling it in a safe way. Cross-site request forgery. Like I said, this is kind of a staple attack. It's like a hammer go-getter. And essentially, this is an attack that tricks a unsuspecting user into performing an action of the attacker's choosing. And this is done against web applications and is performed by an attacker hosting malicious code on an attacker-controlled web server that he then tricks the user into visiting, or compromising some other website and then somehow having the victim visit that website. And what happens is the victim visits the malicious website. Malicious code is then returned to the browser of the victim, and that code is then rendered in the browser, and then a request is sent to the web application server. and any authenticated session information, whether it be a cookie or HTTP basic auth, will be forwarded to that server. And if the end user has permission to carry out the request, then it's going to happen, and the attacker wins. So some countermeasures for cross-site request forgery. Log out of web applications. When you're done doing whatever you're doing, whether it's banking, email, whatever, log out. If the developers implemented session management correctly, when you click the logout, your currently authenticated session cookie should be invalidated, meaning you should no longer be able to use it to access the page. Of course, there is a chance that they did this wrong, and you could still reuse that cookie. And do not save credentials in your browser. Something I should note is if an application is using basic authentication, just logging out doesn't get rid of that information. You actually need to clear the cache and history and all those settings within your browser to actually have it remove those cached credentials. Otherwise, an attacker will be able to leverage the fact that they still exist in your browser. Okay, and then developers. Implement anti-CSRF tokens, and essentially all these is a secret nonce that an attacker has. It is unknown to the attacker, and they're included in as a hidden form value in a form. Both the name and the value are random, so there's two values that an attacker is unaware of, and those values are then validated on the server once a request is sent. And then HTTP referrer checking. Essentially what this does is checks the referrer of the request coming from a client, and if that referrer is outside of the origin of the current application, it'll deny the request. Now, in the past, there have been ways to bypass this. You were able to use things such as Adobe Flash or I guess even Silverlight to basically forge the referrer header. But for a couple of years now, that hasn't been possible because the referrer header is now on a disallowed list of headers that can be modified. And then if you're feeling ambitious, have the end user re-authenticate before performing any action that performs a state change. All right. Sorry, guys. I'm getting over a cold. I apologize. The next thing we're going to talk about here is missing function level access control. So this picture pretty much explains it. You have a road with a gate, but people just kind of go around the gate. Like, who cares? I don't care. And basically, this vulnerability is just the absence of server-side authentication and authorization checks, meaning that you may be able to access restricted content without authentication, or maybe you're authenticated, but let's say as a regular user, aka a non-administrative user. But that regular user then has the ability to call the REST API that may be used by the admin user and carry out administrative functions. Again, that can be detrimental to the integrity of the application. So really, the biggest thing here for countermeasures is to perform these checks. Any action that is sensitive within the source code, you should be checking to see if the currently logged in user has permission to access it or perform it. And if they do, allow them to do it. Pretty straightforward. All right, buffer overflow. So this is my favorite type of vulnerability. I love memory corruption vulnerabilities. Like every time I find one and it looks like it's going to be exploitable, I get giddy like a little girl. It's amazing. And these vulnerabilities essentially are catastrophic in the sense that they will allow you to execute any code that you want. You can call directly into the operating system. It's phenomenal. And they happen because, excuse me, developers will trust the input supplied by the application, which essentially was supplied by the end user, and then they take that input and they copy it into a fixed size buffer. And if you can copy more into that buffer than what was allocated, you're going to corrupt adjacent memory. And by virtue of how applications work, how memory and CPUs execute instructions, blah, blah, you'll overwrite sensitive values and data structures and ultimately influence the execution flow of the program. So here I just have a screenshot of a ARM vulnerability that I'm debugging, and as you can see, we had a SIG-SEG-V, which is a segmentation fault, in 44444444. That's 4 Ds. So we were essentially able to control program counter, which in ARM is equivalent to EIP in x86, and this will now allow us to alter the flow of the program and go where we want in memory, execute what we want. So it's great stuff. So countermeasures, developers don't use unsafe functions. So if you're developing in C, you really have to worry about this. If you're developing in Java, you don't have to worry about this, but if you are, let's say, using JNI to where there is native code or various C code, you should worry about those underlying libraries or even the virtual machine that is running your interpreted language. Perform bounds checking. Bounds checking is the action of checking the length of the input that was sent by the user before copying it to a location in memory. This effectively will eliminate buffer overflows in the sense that you're always going to copy just the right amount of bytes to fill that buffer and no more. And then some mitigations that can be used, like a defense in depth, are compile and linking protections. And you should definitely perform these things, such as like canary and stat cookies. And what that does here is basically any string-based function, it'll take a value that's in the .data section of memory and put it into the prolog, and this value will eventually be pushed down the stack. And if it's corrupted, the program will terminate, and that value is checked in the epilogue of the function. So if you overflowed the stack and you overwrote this value, once the function got to the epilogue and performed this check, it's going to crash because the value state has been altered. ASLR, which is address space layout randomization. It's essentially making your code position independent. And what that is doing is basically saying, hey, this program can run anywhere in memory. And that's achieved by basically the calculation of offsets in memory. So no matter what the address is, where you want to go in memory is always going to be at a specific offset. So it's okay for the addresses to change because you know that your code that you want to execute will be at said offset. And then dep/nx, which is non-executable stack. By default, GCC, if you compile a program, the stack is non-executable, meaning that if shellcode or some code was placed on the stack and then you jump to it, you will not be able to execute. It'll cause an error and the program will essentially crash. Now, if there are other types of vulnerabilities or regions within memory that are not marked executable, or you're able to use like ROP, you could call functions such as mprotect to mark a region within memory as executable again. So it is possible to bypass these types of restrictions. Same with ASLR, but we're not going to talk about that today. So the first case study that we'll talk about with demonstration is D-Link. The model DNS 345, as I said, and we are going to exploit two vulnerabilities. Command injection and authentication bypass. If you recall, authentication bypass was a subset of the missing function level access control. So what we're able to do here is basically take a C program that I wrote and point it at this D-Link device and become root, gain a root shell. Something that was kind of neat about this vulnerability, or this exploit, I guess, was the fact that there was no interactive shell, meaning that if we executed, let's say, Telnet or Netcat, and we wanted to have the argument program be like bin/sha, we were unable to do so. The device had a underlying shell that would interpret operating system commands if the web application or the NAS device told it to do so. But if we tried to interact with it interactively, it wouldn't work. It would essentially just hang. Well, so if I have the ability to execute commands, how am I going to, have an interactive shell remotely? The answer to that is shell scripts. So read is very great. Takes data from a file descriptor and puts it into a variable. If you have data in a variable that was coming from, let's say, standard in, which is what the file descriptor you're going to be sending data into if you're at a terminal, and then executing that with the shell interpreter, you essentially have a shell, right? Yeah, absolutely. So that's what we're going to be doing here. Oops. So now I'm going to go over to my virtual machine, and we will own this Netgear device. So really quick, I need to just determine the IP address of this guy, because I always forget it. 1.34. So ping 192.168.1.34. We're golden, great. So we'll go over some of the source code really quick. Oops, not a binary. Can you guys read that okay, or does it need to be a little bit bigger? All right, I'm going to assume it's okay, no complaints. Okay, so essentially what we're doing here, we have all our function declarations. We're really going to be making a web request to the web server to this page, system_mgr.cgi. And within this variable, this HTML or HTTP parameter, f_sender, we're going to execute a series of commands. Well, we're going to make a couple of requests to basically create the shell script on the fly, and then you pass it to Telnet-D as the login program. So when we log in, our shell script will then be executed. And upon execution, we'll be able to supply data to standard input, which is what read is waiting for. That'll then be stored in CMD, and then we are going to execute it with with SH. So we have our post request here, which is going to send this to the router or to the NAS device with the post data that I showed you up here. And for each request, we are going to send one command. So as you can see here, we're just creating our socket and connecting to the device and using all of our fancy cumbersome C to create these various web requests. And once we're done, we are going to connect to the root shell. So we're here. We're going to call system and connect the shell. And shell was at the top. And all it is telnet and then the argument, which is going to be the IP address that we provided on the command line. So if we come over here and we run this puppy, it's going to ask us for the IP address in the port. Well, we determined that that was 192.168.34, and just to confirm, we are on port 80. So we're going to go back over here to 80. Actually, right before we send this, let me just show you that we can't telnet to the device. 192.168.1.34. Oops, 34. See, connection refused. So we're going to send a couple of requests. We're creating that shell script. And then we're connected to the shell. We're dropped in the shell. And as you can see, UID root. So sending 4 requests allowed us to become root on this device. So now we essentially own this device. Anything that's on it, whatever we want to do, it's ours. So just because you have various restrictions in the types of software that's provided on these embedded devices doesn't mean that you can't leverage a vulnerability into performing a full compromise. It just means you have to, as people like to say, think outside the box. Really, anytime somebody says that to me, I always like to ask, well, how big is the box? So yeah, we're going to move on to our next case study now. And this is the Netgear, and it's this device right here. We just exploited this D-Link. It doesn't really matter. This Netgear is a ready NAS. Within the past year, I believe somebody from Tripwire found a an unauthenticated command injection vulnerability in the login page or the password reset page. Well, Netgear actually patched this vulnerability, but like the idiots that they are, no offense Netgear, if anybody works at Netgear in the audience, they basically fixed the one vulnerability, but they failed to audit the rest of their source code. And little did you know, there are a handful more of command injection vulnerabilities. Ridiculous. At this moment in time, I don't have an authentication bypass for it, but this device is susceptible to cross-site request forgery. So basically, I'm going to demonstrate how an attacker can leverage cross-site request forgery to execute commands in the system. And I'm going to launch this from my browser, so it's basically just simulating the attack. We're not actually going to be on separate network segments. And what this will do is open up an HTML file, the code will load, and it's going to submit a bunch of XML to the Netgear device and execute a command. We will then receive a reverse shell on a port that we are listening on. Now, cross-site request forgery is essentially pretty easy to develop an exploit for. In the simplest of cases, you're essentially just calling the REST API, so you're basically forging an HTML form that would be on the application. It becomes more tricky if you start having to deal with things like XML or JSON data, because you have to start worrying about specific content types. And XML, you actually have to format the form values differently. So you have to look for specific delimiting characters within the XML, see how you can put them within the form, and then make sure that the request that gets sent by the victim's browser is a properly well-formatted XML request. And I'll briefly discuss that when I pull up the source code here. So the only challenge here is tricking an unsuspecting user into viewing your code. And we've discussed a few ways in which you could do that: sending them a link, getting them to browse to your web server where your code is hosted. At that point, they would be owned if they were logged in. This device is using basic authentication, so there are no session cookies. The authentication value is the username, :password, base64, and then put into an authorization header in the HTTP request. So let's go own this device. All right. Okay, so first of all, we will look at the code here. So this is a big blob, and it essentially is XML data. Make it a little bit bigger so you guys can see. And literally all we have is just an HTML document. But what's really important here is the form and then the script. So first we'll talk about the form, which is just going to send a request to DB broker over HTTPS, which this is the only device that I've looked at that enforces HTTPS. So while I was hating on Netgear, I'm also going to give them props at the same time. I mean, that's outstanding. It's very shocking. But anyways, back to the XML blob. So remember what I was saying about having a well-formatted XML request. So within a form, you have a couple of things: the type, the name, and the value of the form. The name could be like XML data, and the value could be the entire XML blob. But the problem is when that's submitted to the server, it won't be well formed. There'll be some extra unnecessary characters that were created and put there by the HTML form. So you actually have to break these, break the request up. The extra character would be an equal sign. So you have to break the XML data up on a delimiting character where there's an equal sign. And you can do that under the XML version. So as you see here, we have name, XML version. There is no equal sign. Why? Because when a form is submitted, you'll have the value of the form value, and then the name of the form value equals and then the value. So when that is concatenated with the rest of the XML blob, we will have a well-formed piece of XML. So that's a neat little trick. So we have XML version, and then value 1.0, and we're sending this blob. You see my email address in there. But right here, under server, we have a command that we're executing. And we are basically going to execute netcat, connect back to us on port 31337, and upon doing so, we are going to execute bin./sha. So, with that said, a couple of things here. First of all, we are going to, actually I'll just exit out of this. We will exit out of the code. We will do netcat listen verbosely on port 31337. Before we do that, let me just show you my IP address. Okay, as you can see, 1.77. So netcat listen verbosely on port 31337. Oh, my voice is starting to go. Crap. We will come over to our browser now, and I believe my web server is running, which it is. So we have that readynas.html file. Before we click on this is going to simulate the cross-site request forgery attack. We're basically going to request from the malicious attacker web server the HTML code, comes down to the browser. The JavaScript and the script tags will submit that form that I showed with the XML blob to the D-Link device. The D-Link device will then process it, and we will execute commands. But in order to do that, we need to be authenticated. So let's ensure that we are authenticated, which it appears we are not. So we'll click through the certificate warning, and we will now authenticate to the device. And just to make sure. All right, so we're authenticated. We're fine and dandy. Wait, where to go? We do have our listener 31337. So I guess let's just make this window smaller so you can see it. It should come in at the bottom. So we're going to click this, and as you can see, we received a connection from the Netgear. Well, little do we know, we're root. So we now have another root shell, and this time, instead of being able to send a request directly to the device, bypassing authentication, we piggybacked on the authenticated user and said, hey, you know what, you're going to give me the root shell. And little did they know, upon navigating to our page, they executed a command. So we used a cross-site request forgery vulnerability to take advantage of an unauthenticated command injection vulnerability. And by virtue, we assume full control of this device. No questions asked. It's owned. So yeah, we can do anything else that we want, but that's all right. Onward. All right. So case study, Buffalo. This is the TerraStation 5600. This is a big device. It has like 8 drives in it. And we're exploiting 2 vulnerabilities here. Again, another command injection. And you guys notice the theme here? Remember how I said the most prevalent vulnerability, command injection? All these demonstrations are command injection. It's terrible. I think I had a couple of routers with command injection, not every single one. And the second vulnerability will be, is an unauthorized API call, and it's just a missing check. So again, this is a subset of the missing function level access control vulnerability, to where we are actually going to be an authenticated user, but we are going to call administrative functionality. And this one's really great because this device has 2 built-in accounts: admin for administrating the device, and guest. And the guest account is used for allowing people to access publicly shared files. Well, little did they know they messed up. So this one isn't a live demo. It's actually a video, and as the video is playing, I will narrate and try and describe what's going on. I tried to make it as clear as possible, but I'm sure that there'll be some uncertainties, so we'll see. And that challenges actually is a mistake. That should not be there. Okay. So what we're doing here is we're actually logging into the device, and by logging into this device, I'm just demonstrating that we have an administrator account, and then I'm showing the SID value, which is a cookie, and this is a unique value that is supposed to be used for authentication, which we will find that it isn't, and then also used within the JSON RPC call. So we log in. This device was a little bit slow. I tried to cut out some of the dead space. So we now logged out. We're going to specify a username. We're going to log in as the guest user. Any day, Buffalo. All right, so we're logged in, and notice on the screen it says user ID 20. Every user has a user ID, and every created user will have user ID. It's like 1001, 1002, etc. You know, very similar to the underlying Unix system. Well, it is identical actually because the accounts come from that file. So as you can see, we have a SID file, or a SID value, and I attempted to telnet to the device. We were unable to do so. So we have a series of requests. As you can see, I have a SID value here. This method that we're actually calling is user.edit, user ID 52, which is the admin user. Remember, the guest account was 20, and then we're going to change the password. So just clicking go without updating that value demonstrated that we were unable to execute the action. What? Oh, we are really? Holy cow. Guys, I'm terribly sorry. I completely talked too much. I guess we're actually out of time. I was not paying attention. So I guess that we're definitely going to have to cut this short. Yeah, I actually have an elapsed time here as well. Do we have any QA time normally?
We can do that out in the hall.
Okay. All right. So we actually got to cut this short. So, yep, that's it, I guess.